right, in the last chapter we talked about statistical mechanics, and we're going to come back to that briefly, but we're now moving on to chapter 9, where we're going to pretty much finish everything that has to do with thermodynamics for this class. We're sort of reaching the pinnacle of thermodynamics in this chapter, because we're going to start talking about the free energies, Helmholtz free energy and Gibbs free energy, which are a lot of the main, most important quantities for chemists. So in previous chapters we've seen that the second law of thermodynamics says that for an isolated system, the condition for equilibrium is that the entropy has to, of the system necessarily now, because it's isolated so the surroundings don't do anything, the system entropy has to be a maximum at equilibrium. That means that if a small change in the system causes a small change in the entropy, and that change turns out to be 0, then you're at equilibrium. If that change turns out to be greater than 0, then whatever small change took place will occur on its own. It will be spontaneous as done in the forward direction, in other words. On the other hand, if we get a negative quantity, then it's not that it won't happen, it will happen in the opposite direction. The backwards process will be spontaneous. All that's true for an isolated system. What about for an open system? We haven't talked very much about that so far, except to point out that if the system is open, the second law still applies. It's just that it's the entropy change for the universe that we have to look at. That is the sum of the entropy change for the system and the entropy change for the surroundings. That, all the rules above apply. They just apply to the total entropy for both system and surroundings, not just to the entropy of the system alone. And we could do all the calculations this way, and I think for a long time in the 19th century, people did do these calculations that way. But easier ways were found, and that's what we're going to talk about. The easier ways involve these free energies, Gibbs free energy and Helmholtz free energy. So let's look at that. Let's consider two situations. The first one, where the system in question has a temperature bath in the surroundings, and it's got non-insulating walls, so the temperature bath keeps the temperature constant in both system and surroundings. And it has a fixed volume, that is, it doesn't have a plunger or a piston that allows the volume to change. And the second case, where there is a plunger or a piston, and there's a temperature and a pressure bath in the surroundings. It turns out that the important quantity in the first case is something called the Helmholtz free energy, which I imagine people here haven't heard very much about before. And in the other case, it's the Gibbs free energy that's most important, and I know everybody here has heard about that and used it, in fact, in freshman chemistry. Let's begin with this second case, because that's the most important one for us, and so we'll focus on that. The Helmholtz free energy is used a little bit by proper thermodynamics experts and so on, actually a fair amount, but the Gibbs free energy is used much more often. The primary reason for looking at the Helmholtz free energy in this class is that it provides us a neat and nice way to make connection with the statistical mechanics that we talked about in the last chapter, and we'll see about that later on in this lecture. So beginning with the second case, we have a temperature bath and a pressure bath. We're considering entropy changes, some kind of changes taking place. And there's an entropy change associated with that in the system and also in the surroundings. The total entropy change is, of course, the sum of these two. This one we're going to take to be a given or a known quantity. That's something we'll have to calculate on a case-by-case basis. But it turns out we can say something about the surroundings entropy change in a general way that doesn't have to be recalculated on a case-by-case basis. So let's do that. The entropy change for the surroundings is whatever heat change took place, whatever reversible heat change took place. Let me write that into the notes here. Reversible surroundings heat change. divided by the temperature. Since there's a temperature bath out in the surroundings, that temperature is a constant. And another thing I should fill in there. All right. If it's a reversible process, which it has to be, right, for the purposes of calculating entropy changes, then the entropy change for the surroundings is equal to the negative of the heat change for the surroundings is equal to the negative of the heat change for the system. And for a constant pressure process, and we've got a P bath, so it must be a constant pressure process, a P bath and a reversible process means it has to be a constant pressure process. Then that heat change for the system is the same thing as the enthalpy change for the system, and the enthalpy is a state function. So in this case, the heat change is a state function. The heat change for the surroundings is a state function because it's the same thing as the heat change for the system, which is the same thing as the enthalpy for the system, except for a minus sign. That means that the entropy change for the surroundings is equal to minus the enthalpy change for the system, remember, divided by T. And that means the entropy change for both system and surroundings is ds minus dH over T. And now I'm going to multiply both sides by the quantity minus T. And you may say, why do you want to do that? And it isn't necessary. In fact, this really is enough to go with right now. We could just use the second law in the normal way, but it's traditional to multiply by minus T. And that gives us a quantity on this side which is proportional to the entropy of the universe. It's not the same thing as the entropy of the universe. But since we're talking about a constant temperature situation, this thing that we're multiplying by is a constant, so it doesn't really make very much difference. The main thing that makes a difference is that minus sign, as we'll see later. And that means that on this side we get dH minus TdS. Temperature is again a constant, so it's just d of H minus Ts, that whole quantity. And we can call that quantity in parentheses by a new name. We call it Gibbs free energy, G. And so what we have is that for a constant temperature, constant pressure process, the change in the Gibbs free energy for the system, notice, no subscript. This is the enthalpy change for the system. This is the entropy change for the system. This is the temperature for the system because there's a T bath and it's therefore also the temperature of the surroundings. But all these are system quantities, and that means that this Gibbs free energy quantity is also a system property. But it turns out that its change, the small change, is equal to the small, well, it's proportional to the small change in the total entropy for both system and surroundings. And so we make a definition. We call this new quantity Gibbs free energy H minus Ts. And like I was just saying, it's a system quantity. And what all this stuff up above has just shown is the important fact that for a constant temperature process, but not for other kinds of processes, it has to be a constant temperature, constant pressure process. The change in the Gibbs free energy is proportional to the change in the total entropy for the universe. If it's not a constant temperature, constant pressure process, then we can still calculate what that delta G or dG quantity is, what the change in Gibbs free energy is, but now it doesn't have any particular special meaning anymore. The Gibbs free energy was designed to be used for constant temperature, constant pressure processes, and so it can be talked about in other cases, but it doesn't have any particular meaning in those cases. So if this relationship is true, then we can talk about the second law now, where we can restate the second law in terms of Gibbs free energy for these special cases, for this special set of circumstances. For a constant T, constant P process, then, for a process in the presence of temperature and pressure baths, the Gibbs free energy being a minimum, because of the minus sign, right? If this is a maximum, then the Gibbs free energy is a minimum at equilibrium. So a maximum in the entropy for the universe corresponds to a minimum in the Gibbs free energy for the system. If the Gibbs free energy change is less than zero, then again, because of the minus sign, a negative Gibbs free energy change is favorable. That means the process that caused that change will go spontaneously on its own in the forward direction. If the Gibbs free energy change is 0, then we're at equilibrium. And if the Gibbs free energy is positive, if the Gibbs free energy increased, then that's heading away from the minimum, right? And that means that the process wants to go the other way, and it'll be spontaneous. The process will go the opposite direction. It'll go backwards spontaneously. Very often in other classes, especially freshman chemistry, you've seen this expression, which is just the same as this expression up here, this one up here, actually, except that I'm using finite changes, deltas, instead of differential changes, d's. And it's the standard relationship I think probably everybody's seen many times. Delta G equals delta H minus T delta S. Probably, well, at least by the end of this class, you'll be able to recite that without, without even blinking. And let's look at the pieces of it. Delta G is then proportional to the total delta S change for the universe. Delta H, if we look at where that term came from, it came from keeping account of the entropy change for the surroundings. So delta H here is not the same thing as the entropy change in the surroundings. The entropy change in the surroundings, in fact, would be equal to minus delta H over T, but it's keeping account of the entropy change. It's accounting for, dealing with the entropy changes in the surroundings. It's accounting for the effects of entropy changes in the surroundings. The T is the common temperature for both system and surroundings, and then delta S is specifically the entropy change for the system itself. Let's look at some examples to see how this works out, because the two ends of the Gibbs free energy, basically the delta H end and the delta S term, tend to go in opposite directions. And whether or not a given change is like a chemical reaction, for example, is spontaneous depends on the sign of delta G. If delta G is negative, then the chemical reaction, let's say, will go in the forward direction. If it's positive, it'll go in the reverse direction, and if it's 0, then it's at equilibrium already. And so whether we get a positive or a negative or a 0 answer depends on the relative sizes and signs of these two terms. And so let's look at what those things look like in a couple of cases. First, let's consider a very simple chemical reaction. A single H atom and a single chlorine atom combining to form HCl. We looked at this particular special case earlier, and I said in that case that it was driven by entropy changes in the surroundings, right? Which means in this case the delta H for the system, which gives rise to a big Q change for the surroundings. In this case, we know that since a strong bond is being formed, that the delta H is all that bond energy being lost to the surroundings, and so it's the heat of reaction, and it's very negative. This is an exothermic reaction. A negative delta H means an exothermic reaction. That means heat is being lost to the surroundings. That means the entropy is being raised in the surroundings, and that's the reason this reaction goes spontaneously. There is also an entropy change for the system itself, but that's unfavorable, right? We're going from 2 free atoms to 1 free molecule. That represents a loss in degrees of freedom, or the ranges of degrees of freedom for the system. So we know that the delta S will be a negative. The entropy change for the system will be unfavorable. And if we look at the two ends of delta G, then we're going to get a large negative term for the delta H contribution. And when we look at the minus T delta S contribution, that will be positive now, right, because delta S is negative, and it will be smaller. So between the two of them, this term wins. We get a very negative delta G overall. The reaction is spontaneous. Again, you can see that there's a trade-off in the two ends. The delta H term is favorable in this case. The delta S term is unfavorable, but the delta H term is bigger, and so the reaction goes. We'll often see that case, though sometimes the roles are reversed. Sometimes the delta H is unfavorable and the delta S is favorable, but the delta S term is bigger, and so the reaction still goes. Sometimes the overall change is unfavorable and the reaction goes in the opposite direction, and so on. All the possibilities are there. Again, yes, I guess it's worth saying, I've said this quite a bit already, but let me just point out that this business of energy going out into the surroundings, heat going out into the surroundings, is an example of a spreading out of something, either matter or energy. And that always gives rise to a increase in overall entropy. Well, in this case, entropy of the surroundings, which overcomes the small unfavorable change in the entropy of the system. All right, other reactions, especially for a biochemically oriented class like this one, we might want to consider things that aren't just, simple small molecules forming chemical bonds. We want to consider things like this, where protein number 1 and protein number 2 come together and bind. The very fact that they form some kind of binding interaction here says that heat must be released, right? Whatever this quote-unquote bond is that's getting formed, it's not really a chemical bond. It's a whole bunch of weaker interactions that's taking place, a whole bunch of stacking interactions and hydrophobic interactions and charge-charge interactions. We'll look later in the class. We'll look at what's actually causing this binding in more detail. But the very fact that there is a binding means that energy is being released into the surroundings, and that energy release is a favorable quantity. It will mean that delta H is less than 0. On the other hand, the very fact that two things are ending up as only one thing, it's the same, in principle, it's the same thing as what happened up here, 2 atoms going to one molecule, in this case two big molecules going to one even bigger molecule, means that this other term, the minus T delta S term, will be a positive quantity overall, right? The delta S will be negative, but the minus T delta S will be positive, which means it's unfavorable. And so whether this binding reaction takes place or not, depends on the relative size of these two. And again, at the end of the class, when we talk about protein-protein binding and other kinds of changes like that, we'll see that sometimes the binding constant for this reaction is very favorable, in which case the delta H term here was the dominant one, and sometimes it's very unfavorable. It's much, much less than 1, in which case this term was the dominant one. Even if it's unfavorable, it may go to a certain extent, but equilibrium will be reached with very little of this and a whole lot of that if the overall entropy term is the dominant one. All right. Both of these cases up above, delta H was the driving term for the reaction, but it can happen the other way around. Let's consider a dissolving reaction. A dissolving process or an evaporation process or a phase change, these are all quote-unquote chemical reactions for our purposes in this class, because thermodynamically it doesn't matter whether it's a chemical bond forming or some other process happening. All that matters is that entropy is changing and energy is changing, and keeping track of those things means we can use the same thermodynamics no matter whether it's, strictly speaking, a chemical reaction or not. So we're going to treat this dissolving process as if it were a chemical reaction. It is for thermodynamic purposes. So I've got an ordered crystal over on this side, and it comes apart into a whole bunch of dissolved molecules on this side, inside some solvent. In this case, clearly the delta S term is favorable, right? It's going to be positive. Matter is spreading out. And so the minus T delta S term is going to be favorable. It's going to be less than 0. But also all the little interactions that held these molecules together in the crystal are getting broken. We're breaking a whole bunch of quote-unquote small, weak bonds. And they'll all add up, and that means that the delta H term will be greater than 0 and therefore unfavorable. And so the dissolving process happens, or it doesn't, depending on whether this term is bigger or whether this term is bigger. In some cases, either of the two can be the bigger one. Either the crystal does dissolve, in which case this term was the big one, or it doesn't dissolve, in which case this one was the big one. Or it doesn't dissolve very much, right? It's just like the chemical reaction. If it's unfavorable, it still goes to a small extent, and we'll talk about that. But it won't go very far. All right. A third example here is where I have two proteins binding together, and we're not considering for the moment the overall binding process. We're considering what's happening to bound water molecules that are stuck to the surface of the protein. It turns out that for a lot of interactions, a lot of protein-protein binding interactions especially, there are water molecules that are bound pretty tightly to the surface. They're not chemically bound. They're bound by hydrogen bonds and by other kinds of interactions, but they're pretty immobile, which means they're stuck there pretty hard. And in order for the proteins to come together and form a new interface with each other, some of those waters have to be lost. So that water right there has to be lost, that water, that water, that water, and all these waters in the middle here have to be lost. And that means that even though the entropy change for the two protein molecules, considered by themselves, is unfavorable, right? We go from two molecules to one. Well, we're releasing a whole bunch of bound water at the same time, and so we're releasing, in this case, 7 water molecules that were pretty tightly bound before. Now they're free to run around. So the question is the entropy change really negative, or is it possibly positive? We don't know. It depends on the relative size of the water release terms and the protein binding terms. For some reactions, the water release terms may be the dominant one, in which case the overall entropy change is actually positive, is actually favorable for this reaction, even though it looks at first glance as if it should be unfavorable. All right, that is the Gibbs free energy. There is another kind, actually there's a bunch of different kinds of free energies. You can define free energies for almost any situation if you like, but we won't talk about that. That's for high abstract thermodynamics classes. And this is really an introduction to thermodynamics, so we won't talk about those. But there's another common kind, and that's the Helmholtz free energy. That's the one that applies when the situation is just slightly different from last time. We have a temperature bath in the surroundings still, but no P bath and no piston, so the volume is fixed. And so it's constant volume, constant temperature processes for which the Helmholtz free energy is especially useful. Again, we want to calculate the total entropy change for both system and surroundings. And again, the thing that we can deal with profitably is the change in the surroundings entropy. Again, it's the change in the heat for the surroundings over the temperature for the surroundings in the T bath. But in this case, the energy change, assuming that there's no PV work, well, there's only PV work, so that means there's no other kind of work, and that means there's no work at all, right? Because if the volume can't change, then the PV work is 0. In that case, the heat change for the surroundings is just equal to minus the energy change for the system, right? It's all heat change. So anything gained by the surroundings is equal to the energy change, the total energy change for the system, with a minus sign. And now plugging that expression back into the expression for the total entropy and multiplying by minus T on both sides, we get that minus T delta S of the universe is now du minus TdS, which is the differential of the quantity U minus Ts. And so we make the definition very similar to what we did for Gibbs free energy. We define this new quantity called the Helmholtz free energy. As U minus Ts. You can see the only difference between Helmholtz and Gibbs is that Helmholtz has energy here and Gibbs has enthalpy there. And the only real difference is that in this case, where there's no PV work going on, it's energy that's relevant, whereas in the Gibbs case, Gibbs is more common because the experimental conditions are more common. You don't usually have constant volume. You usually have constant pressure. But the Helmholtz free energy is actually a little bit simpler otherwise, right? There's no PV work going on. That simplifies things. In the case of Gibbs free energy, it's enthalpy that's here because enthalpy is equal to U plus PV. And that plus PV term is canceling the minus PV term that's inside of energy. It's accounting for the work that was done, the pressure volume work that was done. Well, there's no need to account for pressure volume work in this case because there is no pressure volume work. All right. So Helmholtz free energy is very similar to Gibbs free energy, and a lot of the same things we said about Gibbs free energy applies here too. First of all, that for a constant volume, constant temperature process, change in Helmholtz free energy is the same thing, or it's proportional to the change in the entropy of the universe for both system and surroundings. If we're at equilibrium, then Helmholtz free energy will be a minimum rather than a maximum for entropy, and vice versa, right? If Helmholtz free energy is a minimum, then we are at equilibrium. If the change for a given process, small process, in Helmholtz free energy is less than 0, then that's a change that will happen spontaneously forward. If it's equal to 0, then we're at equilibrium. That's the condition for equilibrium, in fact. And if it's greater than 0, that's unfavorable, and the reaction will go, or the process will go in the backwards direction spontaneously. All right. So all that's almost the same as for Gibbs free energy, but now we come to something new, and this is really the main reason for talking about Helmholtz free energy. And that is that Helmholtz free energy has a close connection with the statistical mechanics, with the canonical Boltzmann distribution that we talked about in Chapter 8 last time. We saw I said many times last lecture that this quantity Q, the partition function that comes from statistical mechanics, is important in its own right. I said that it was related to Helmholtz free energy, and now we know what Helmholtz free energy is. Let's talk about what that relationship is. From the Boltzmann relationship for the entropy of the universe, that has to be equal to the Boltzmann constant times the logarithm of the number of microstates that's available to the universe, to both system and surroundings. I won't go through it again, but last time we pretty much showed, I didn't point it out or emphasize it or anything, but here I will emphasize it, that the number of microstates available to the universe is proportional to the sum over all energies of the system of the number of microstates for each energy of the system times this exponential factor that accounts for the number of microstates in the surroundings, e to the minus beta u. So this is surroundings microstates, or it's proportional to surroundings microstates, and that's why it appears in this sum. And we're summing over all the energies, which means we're considering all the possible situations, and that's why this is proportional to the entropy, the number of microstates available to the universe. But if that's true, then this quantity is just the partition function. It's just this Q that we talked about last time. We calculated partition functions for at least some simple cases last time. Fairly easy to calculate, at least in those simple cases. And that means we can substitute this up into here, except for an overall constant, which turns out is 1. And that means that the minus T times the change in the entropy of the universe, or times the entropy of the universe, is equal to minus kBt times the logarithm of the partition function. That's just this up here again, a little bit rewritten. And this is the Helmholtz free energy from our definition above. And so we have that the Helmholtz free energy change for a constant temperature, constant pressure process is equal to minus kBt. Notice there's an extra t in here now, and a minus sign, times the logarithm of the partition function. So the partition function, we said last time, was the effective number of states available to the system, but it turns out to also be the effective number of states available to the universe. Or actually, the actual number of states available to the universe, not just the system. And hence its value, hence its usefulness for calculating thermodynamic properties. We won't talk about this too much in this class, but both Helmholtz free energy and entropy and Gibbs free energy, these are all fundamental thermodynamic potentials. If you know S or A or G as a function of their natural variables, and we'll talk about that a little bit more further down, then you can predict every possible thermodynamic property for the system in question. And what this is saying is that if I know the partition function for the system in question, then I can get A. And therefore, the partition function is also equivalent. Knowing the partition function is equivalent to knowing all the possible thermodynamic properties of the system. And so, if Q can be calculated from microscopic properties, and we know how to do that, right? It's a matter of doing this sum of e to the minus beta u sub I. It's a matter of summing up all these exponentials over all the possible microstates of the system. If you can do that sum, a lot of times you can't do that sum. It's just impractical to do. But in some cases you can. And if this were a class on stat mech, or if we just had more time in this semester, we'd do examples like that. There are cases, lots of very useful cases, where you can do it. And if you can get that Q from the microscopic properties, then you can get all the thermodynamic properties for that same system. It's a way of going from knowledge of the microscopic composition of your system, say a bunch of water molecules, to accurately predicting, in fact, in a lot of cases, all the thermodynamic properties of the system. I say here that we won't do very much of this, in fact, almost none of this, just because we just don't have enough time. But I want to encourage people. I emphasize this at this point in the class every year because it's good for people to know that this is possible. It isn't, thermodynamics is not a black box that you sort of just hand wave and get things. No, you can predict thermodynamic properties and understand where they come from in detail from the microscopic properties of the molecules involved. Again, we won't have time to do that. I wish we did. It's a great exercise and very illuminating. It forms a big part of my understanding for this whole area. But we just have to prioritize, and there isn't enough time this takes quite a bit of time, and there just isn't enough time in the semester. All right. That is the end for this lecture. We'll come back and talk about this overview of all the thermodynamic properties in the next lecture.